So one of the most important things about the connection between volcanoes and the climate is that the impact on the atmosphere is 6 months after the eruption. Now, why does this happen? Again, it's kind of counterintuitive. So when we have the eruption of the volcano, we have this jet of material coming out of the earth, whether it's lava, gases, even water vapor, steam, particles, the ash, and we have this massive eruption which goes up into the atmosphere and sometimes into the stratosphere. Now, the big particles, as we said, the ash and the larger particles fall out fairly quickly. Within a week or two after the eruption, they're gone. But what happens is that we have gases in the upper atmosphere, in the stratosphere, and particularly we have the gas called sulfur dioxide, SO2. And this gas reacts both with oxygen and with water and forms tiny little droplets of sulfuric acid. So the gas gets converted to little droplets of sulfuric acid, and these droplets are very bright. They're very actually white in color, and these droplets reflect the sunlight back out to space. This takes time for the sulfur dioxide to be converted to sulfuric acid, and this whole process takes about 6 months. And so initially we have a very large concentration of sulfur dioxide, but this doesn't impact the climate because it's a gas. Once it gets converted to droplets of sulfuric acid, those droplets are what impacts the climate by interfering with the sunlight coming in to the surface. And this sulfur dioxide, once it's in the stratosphere, will spread around the planet and slowly again get converted to these droplets. It then actually will get spread north and south away from the location of the volcano, and eventually will produce a veil of these particles which covers the whole planet. And so while we have these particles, we're reducing the amount of energy which is coming to the surface, and hence we have a cooling. On the other hand, in the actual plume where we have these droplets, some of the solar radiation is actually absorbed, and therefore in the stratosphere we actually see a warming, increasing in temperature, while at the surface we see a decrease. We're going to have another schematic description here when we have the large eruption of the volcano. And again, not all volcanoes, only ones which will take material up to 20-30 kilometers in the stratosphere, like Pinatubo, like El Chichon. A lot of the big particles, the ash, will fall out immediately. But even once the volcano stops the eruption will be over. We're left with this gas, the sulfur dioxide in the stratosphere. And this then slowly gets converted to tiny droplets of sulfuric acid, which reflect the sunlight and reduce the amount of radiation coming in and coming to the surface. So at the surface, we see a net cooling. But at the same time, in this layer where we have these droplets, we have absorption both of some of the sunlight coming in and some of the Earth's radiation going out. And therefore, we have a net heating in the stratosphere. And this is a very clear sign of this climate impact, cooling at the surface, heating up in the stratosphere because of these aerosols which are interfering with the radiation balance of the planet. So here we can see some data, first of all, of the sulfur dioxide, this gas which comes out of the volcanoes. On the top left, we can see the day of the eruption, the 16th of June, 91, then the 19th of June, 22nd, 25th of June, how this gas is spreading with the winds in the atmosphere and in the stratosphere around the planet. Initially, it remains mainly in the tropics because that's the location of the volcano. But within a few days and a week, we have the sulfur dioxide spreads all the way around the planet. We can compare also the concentrations from El Chichon in the top plot with Pinatubo. You can see the dates here in April 82 and in June 91, and the concentration of sulfur dioxide measured by satellites in these regions. We can see the triangle, at least for Pinatubo, we can see the location of the volcano here, and I think there's also, we can see El Chichon, this little white triangle over here. So now we can see the situation of the sulfur dioxide in the atmosphere on the 21st of September 91. So we're talking about a few months after the eruption, where we have high concentrations of sulfur dioxide, but still mainly in the tropical zone, But slowly this will also firstly be converted to the droplets of sulfuric acid, and it will be spread north and south of the tropics towards the polar regions. And when we look at the particles, we see that if we look at how many of these particles we have in the stratosphere before the eruption, on the top left, the dark blues and the black show that it's very, very clean, very few particles. If you look at the scale at the bottom, it's a log scale. So we have very clean atmosphere before the eruption. We're talking about April, May 91. And then we see June, July 91, the top right, all of a sudden the increase in these particles in the stratosphere, these very small sulfuric acid particles showing in the maximum concentration in red, 2 orders of magnitude or more than we normally see. And then we can see in August, September, the bottom left, where things are spreading out. And when we look in 1993 to 94, we're talking about 2 years, 3 years after the eruption in the bottom right. The colors of green show that we still have an order of magnitude more particles and spread globally over the whole planet than we had before the eruption. The white areas on the plot are simply where we don't have data, since the satellites don't measure in those parts of the planet, but the veil of these particles is truly global in extent, covers the whole planet, and therefore we have this thin veil of particles which are reflecting the sunlight back to space. We can again use lasers, lidars shining light up and seeing what comes back to us, and here we can see at different altitudes in the atmosphere as a function of day after the eruption of Pinatubo. So again, 200, 300, 365 is 1 year after the eruption and going out to 800 days. And the x-axis, the y-axis is the actual size of the particles. So we see that the particles that remain for a long time in the atmosphere are very small, talking about less than half a micron in the size of the particles. There is variability and changes with altitude, but we see that these particles remain in the upper atmosphere levels from in here 16 to 24 kilometers for years after the eruption. We can also see this from space. So from both the space shuttle took images and from the space station today. If we look at an image looking at the limb of the Earth, so looking at the edge of the Earth from space in 84, so on the top plot is before the eruption of Pinatubo, and the bottom plot is after the eruption of Pinatubo. What we see when we look at the edge of the Earth, like we're looking at the sunset, you see the reds and oranges of the sunset. You see clouds which go up to just in the troposphere, so the top of all these clouds is maximum altitude, maybe 20 kilometers. And above that, in the top image, very clean, but in the bottom image, we see these layers. You can see 3 layers, which are these aerosol particles from the volcanoes, produced mainly by the sulfur dioxide, which has been converted to sulfuric acid. So from space, we can very clearly see these layers of aerosols in the atmosphere. And again, these are blocking out some of the sunlight and resulting in a cooling at the surface. It's interesting just to point out that this painting by Edvard Munch, called The Scream, which I'm sure most of you know about, was painted in 1893. And people claim this was based on Munch's memory of the brilliant sunsets which occurred following the eruption of Krakatoa in 1883. It turns out that the more particles we have in the upper atmosphere, the more brilliant the sunsets are. After the Pinatubo eruption, we had very beautiful sunsets, deep purples and reds in the atmosphere. And so it's possible that Munch was also influenced by the color of the sunsets after the eruption of Krakatoa in 1883.